Welcome. Today, we're diving into the basics of chiller efficiency, breaking down key terms like COP, kW per ton of refrigeration, and refrigeration effect. This beginner's guide is designed for new engineers ready to understand energy optimization in cooling systems. Let's get started with the fundamentals behind compressors, cooling towers, and how they all work together. Today, we're diving into how to properly calculate chiller efficiency, a must-know for every HVAC engineer. When efficiency drops, power consumption goes up, electricity bills rise, cooling capacity falls, and compressors work harder. That means shorter equipment life and higher maintenance costs. In big HVAC systems, chillers can use between 40 and 60% of a building's total electrical power. They're some of the biggest energy users in places like hospitals, malls, airports, and data centers. Understanding this is key to smarter, more efficient cooling. Let's talk about chiller efficiency, a key measure of how well a chiller converts electrical power into cooling. If a chiller uses less electricity but still delivers the same amount of cooling, it's more efficient. For example, one chiller might produce 1,800 kilowatts of cooling using 600 kilowatts of power, giving it a coefficient of performance, or COP, of 3. Another might do the same cooling with only 300 kilowatts, doubling that COP to 6. The higher the COP, the better the chiller is at turning energy into cooling. Let's start by breaking down how a chiller works. Most of the electrical energy powers the compressor motor. That's the heart of the system. The refrigerant moves continuously through several key parts. It absorbs heat in the evaporator, then passes through the expansion valve where pressure drops. Next, heat is rejected in the condenser before the compressor raises pressure and temperature again. Before we dive into efficiency calculations, it's crucial to grasp this basic cooling cycle. Let's walk through the step-by-step process of how this system works. It starts with warm return chilled water entering the evaporator, where the refrigerant absorbs heat and cools the water before it's sent back to the building. Then, the compressor kicks in, compressing the refrigerant vapor and raising its pressure and temperature. This is where electrical energy is used. Next, the condenser releases that heat to the atmosphere, often using cooling tower water or air. Finally, the refrigerant pressure drops through the expansion valve, cooling the refrigerant again, and the cycle repeats. Let's talk about COP, the coefficient of performance. It's a simple ratio that tells us how efficient a chiller really is. We take the cooling output, the amount of cooling produced, and divide it by the electrical power input, or the energy consumed. So COP equals cooling capacity over power input. The higher the COP, the more cooling you get for each unit of electricity used. It's a key metric for understanding chiller efficiency. Let's break down what COP really means. A lower COP signals poor efficiency. That's more energy wasted, higher bills, and potential maintenance headaches. On the flip side, a higher COP means the system works smarter, better efficiency, lower electricity costs, and stronger performance. For example, if a chiller uses 300 kilowatts of electricity to produce 1,800 kilowatts of cooling, its COP is 6. That means for every unit of energy in, you get 6 units of cooling out. Simple, but powerful. When we look at chiller efficiency, or COP, the numbers can vary a lot. It depends on things like load conditions, water temperatures, ambient weather, and how well the system is maintained. Different chiller types have different typical ranges. Older reciprocating chillers fall on the low end. Scroll and screw chillers improve from low-medium to medium efficiency. Centrifugal chillers are generally good, but the high-efficiency magnetic bearing chillers stand out, reaching excellent levels. This comparison helps us see where technology is heading. Let's talk about how we measure chiller efficiency in a straightforward way. We use the coefficient of performance, or COP. It's a simple ratio, cooling capacity divided by power input. Both are measured in kilowatts, which makes the math easy. Cooling in kilowatts, power in kilowatts, just divide one by the other, and you get your COP. This metric method gives us a clear, simple way to understand how efficiently a chiller is working. Let's look at the result of our example. The coefficient of performance, or COP, comes out to 6. That means for every 1 kilowatt of electricity we put in, the chiller produces 6 kilowatts of cooling. That's a solid efficiency for a centrifugal chiller, especially in a commercial setting. We got there by dividing the cooling capacity, 2100 kilowatts, by the electrical power input, 350 kilowatts. This metric really helps us understand how well the system converts energy into cooling. Let's break down how we calculate the coefficient of performance, or COP, using the imperial method. First, we start with the cooling capacity, often given in tons of refrigeration or BTUs per hour. 1 ton of refrigeration equals 12,000 BTUs per hour. To get to COP, we convert that cooling capacity into kilowatts. Then, we use that value to complete the calculation. This process helps us compare chiller efficiency across different measurement systems. Let's talk about electrical power and how it relates to heat energy. 1 kilowatt, or kW, is equal to 3,412 BTUs per hour. That means if you want to convert from BTUs per hour to kilowatts, you divide by 3,412. This conversion is a standard way to compare electrical power with heat energy, helping us understand and measure energy across different systems. It's a simple but essential calculation for anyone working with energy. Let's walk through calculating the coefficient of performance, or COP, for this cooling system. We start by converting the cooling capacity from BTUs per hour into kilowatts. 6,824,000 BTU per hour becomes 2,000 kilowatts. Next, we take that cooling capacity and divide it by the power consumption, which is 400 kilowatts. Doing the math, 2,000 divided by 400 gives us a COP of 5. This means the system delivers 5 times the cooling energy compared to the electrical power it uses. Let's talk about what controls cooling capacity. It depends mainly on 2 things: the water flow rate and the temperature difference, or delta T, between supply and return water. Cold water at 6 degrees Celsius enters the chiller's evaporator. The chiller removes heat from this water, warming it to about 12 degrees on return. This heat is then sent to the condenser or cooling tower. The refrigeration effect is simply the amount of heat the chiller pulls out of the water. That's the core of how cooling works here. Here, we see the fundamental formula for calculating cooling load, the total heat removed from a system. It's simple but powerful. Cooling load equals the mass flow rate of water, multiplied by the specific heat capacity of water, and then multiplied by the temperature difference between return and supply water. This equation lets us figure out how much cooling a chiller can provide, based on water flow and temperature changes. It's a key tool for designing and managing efficient cooling systems. Let's break down a simple formula that helps us estimate cooling capacity in HVAC systems. It's based on 3 key factors: the temperature difference, the flow rate of chilled water, and a constant that represents water's specific heat. The formula multiplies these together: 4.187 times the flow rate in liters per second, times the temperature difference in degrees Celsius. This gives us the cooling capacity in kilowatts. It's a straightforward way to understand how much cooling energy is being delivered. Let's walk through calculating the cooling capacity for this system. We start by finding the temperature difference. The water enters at 12 degrees Celsius and leaves at 6, so that's a drop of 6 degrees. We know the chilled water flow is 85 liters per second. Using these values, we multiply the flow rate, the temperature difference, and the specific heat capacity of water. That gives us a cooling capacity of 2,135 kilowatts. This step is key for sizing the chiller correctly in a real-world setting. Here, we're looking at the real-time performance of the chiller on site. The actual operating coefficient of performance, or COP, is 5.47. That means for every unit of power it consumes, 390 kilowatts, it delivers 2,135 kilowatts of cooling capacity. We get this by dividing the cooling output by the power input. This number tells us the chiller is running efficiently, right within the good range we expect. It's a clear snapshot of how well the system is working in practice. Let's talk about what really affects the COP, the coefficient of performance during chiller operation. It's not fixed. It changes all the time. Factors like ambient temperature, refrigerant condition, and fouling inside heat exchangers all play a role. Then there's compressor loading, cooling tower performance, chilled water temperature, condenser temperature, and load variation. Many new engineers assume COP stays constant, but that's not true. Understanding these shifting factors helps us optimize performance and avoid surprises. Let's talk about the optimal zone for chiller efficiency. Most buildings run their chillers between 40 and 70% load for the majority of the year. That's where the system is most efficient. The peak coefficient of performance, or COP, happens in this range. Chillers don't usually run at full 100% load for long stretches. Understanding this helps us design and operate systems that save energy and reduce costs over time. Most buildings spend most of their time running at part load, usually between 40 and 70% of their full capacity. That means part load efficiency matters more than full load efficiency when it comes to saving energy. As cooling demand drops, compressors unload, and power use goes down. This is the way chillers operate most of the year. Full load, on the other hand, happens less often, mainly during peak summer, when the system runs near maximum capacity and consumes more power. Older chillers often run their compressors at full speed, no matter the cooling demand. That means even when we only need a fraction of their capacity, they're still consuming 100% power, wasting a lot of energy. This fixed-speed operation leads to poor efficiency at part load, with the motor always spinning at full RPM. It's a problem that costs us both energy and money, especially when demand is low. Let's talk about energy savings with variable speed drives, or VSDs. At half load, a VFD uses just 30% of power, compared to 85% for a constant speed system. That's a huge 55% savings. But it's not just about energy. These drives reduce mechanical stress, ensure smooth operation, cut down starting current, and improve efficiency at part load. By matching motor speed to cooling demand, modern chillers become smarter, more efficient, and kinder to the electrical system. Let's talk about how speed affects power in compressors. Power doesn't just drop a little when speed slows down, it drops dramatically, following what's called the cube law. Cut the speed in half, and power consumption falls to just 1/8. Even a 20% speed reduction nearly halves the power used. This happens because power varies roughly with the cube of speed. Variable frequency drives take advantage of this, reducing motor speed during low demand, which saves a huge amount of energy. That's why VFDs improve efficiency so much. Let's talk about kW per TR, that's kilowatts per ton of refrigeration. It's a key measure of efficiency in cooling systems. Simply put, the less power you need to cool 1 ton, the better your system is performing. So a lower kW per TR means you're using less electricity for the same cooling output. This makes it a straightforward way to compare how efficiently different systems operate. Keep this number low, and you're on the right track. Let's talk about 2 key ways we measure cooling efficiency. First, kW per ton of refrigeration, or kW per TR, which is actually the inverse of efficiency. So lower numbers here mean better performance. Then there's COP, the coefficient of performance, where higher values are better. Both metrics look at the same relationship, just from different angles. Remember, cooling capacity is measured in tons of refrigeration, and 1 ton equals 3.517 kilowatts of cooling power. The formula for kW per TR is power input divided by cooling capacity. Let's look at how kW per ton of refrigeration relates to COP, or coefficient of performance. Here, kW per TR is 0.64, which means the COP is about 5.5, calculated by dividing 3.517 by 0.64. Remember, a lower kW per TR means better efficiency, while a higher COP means the same thing, better efficiency. They're just 2 ways to express the system's performance, linked by this simple formula. Understanding this relationship helps us compare and optimize cooling systems more effectively. Let's take a closer look at efficiency in a water-cooled centrifugal chiller. Here, the key measure is kilowatts per ton of refrigeration, or kW per TR. In this example, the chiller delivers 500 tons of cooling while using 320 kilowatts of power. When we divide power by cooling capacity, we get 0.64 kW per TR. This number tells us the chiller is running efficiently, a solid benchmark for this type of equipment. It's a quick way to gauge performance at a glance. Let's take a closer look at chiller efficiency, measured in kilowatts per ton of refrigeration. Lower numbers mean better performance, less power used for the same cooling output. Values between 1.1 and 1.4 indicate poor efficiency, which we want to avoid. Average efficiency falls between 0.8 and 1. Good efficiency ranges from 0.55 to 0.75, while anything below 0.55 is considered high efficiency, the sweet spot we aim for. This scale helps us quickly gauge how well a chiller is performing. Let's talk about how condenser water temperature impacts efficiency. When the temperature stays between 28 and 30 degrees Celsius, the system runs smoothly. The compressor doesn't have to work as hard, pressure stays manageable, and power consumption drops. That means better efficiency with a higher coefficient of performance. But once temperatures climb above 35 degrees, everything changes. The compressor strains, pressure rises, power use spikes, and efficiency falls. Keeping condenser water cool is key to running efficiently and saving energy. Let's talk about cooling towers and how they impact chiller efficiency. Even a slight rise in condenser water temperature can cause power use to spike. That means the chiller's coefficient of performance, or COP, takes a hit. Common problems like incorrect water flow, scaling, fan failure, low airflow, or dirty fill media all reduce tower performance. When the tower struggles to transfer heat to the air, the chiller works harder, and that drives up energy consumption. It's a chain reaction we can't afford to ignore. Let's talk about chilled water delta T, the temperature difference between supply and return water. When this difference is low, around 2 to 3 degrees Celsius, it's a problem. It means the system is working harder, pumping more energy, but with less efficiency and poor cooling. A good delta T is between 5 and 7 degrees. For example, if supply water is 6 degrees and return water is 12, that 6-degree difference signals the system is running well. Getting this right matters. Regular inspection and maintenance are key to keeping chillers running efficiently. Most common problems can be caught early this way. Each issue we see here, from dirty condenser tubes to refrigerant leaks, reduces performance and drives up energy costs. Whether it's excess refrigerant causing poor heat transfer or sensor errors leading to incorrect operation, these faults all chip away at the system's efficiency. Staying on top of these helps maintain a high coefficient of performance, saving energy and money. To keep an HVAC system running smoothly, regular monitoring is key. It helps us catch problems early before they turn into costly breakdowns. A new engineer should focus on several critical areas. Compressor safety, including oil pressure, is a must. We track capacity through water flow rate and system health by checking refrigerant pressure. Electrical condition means watching voltage and current closely. Heat rejection involves monitoring condenser water temperature while building load ties to chilled water return temperature. Finally, cooling performance depends on chilled water supply temperature. Together, these parameters tell the full story. Let's talk about the real impact of proper maintenance. When we keep everything running smoothly, from replacing filters and calibrating sensors to cleaning cooling towers and treating water, we see higher efficiency, or COP, and lower energy costs. It also means our equipment lasts longer. Each step, like checking oil quality or cleaning tubes, plays a crucial role. Preventive maintenance isn't just a checklist, it's the key to better performance and saving money over time. Let's talk about saving energy with chillers, a crucial part of any cooling system. First, keeping the condenser water temperature just right can boost efficiency. Using variable frequency drives helps cut power use when demand is low. Cleaning heat exchanger tubes improves heat transfer, while maintaining proper water flow keeps everything running smoothly. Avoid overcooling by setting the chilled water temperature correctly. Operating multiple chillers properly and maintaining the cooling tower also play big roles in improving heat rejection. Together, these steps make a real difference. Let's clear up a common confusion. Capacity and efficiency aren't the same thing. A chiller might be running at full capacity, delivering all the cooling it promises, but still be inefficient if it's using too much power. Efficiency measures how much energy it takes to produce that cooling, often shown as COP or kW per ton of refrigeration. Capacity, on the other hand, is simply how much cooling the chiller provides. Understanding this difference is key to optimizing performance. Let's look at two chillers side by side. Both deliver the same cooling capacity, 1800 kilowatts, but their efficiency is very different. Chiller A uses just 300 kilowatts of power, giving it a high coefficient of performance, or COP, of 6. Chiller B, on the other hand, consumes 420 kilowatts with a COP of only 4.28. That extra 120 kilowatts means higher operating costs and wasted energy. This example shows why efficiency matters. It's not just about output, but how much power you use to get there. Let's clear up a common misconception about chillers. Unlike regular electrical heaters, which can't be more than 100% efficient, chillers actually move heat instead of creating it. That's why their coefficient of performance, or COP, is greater than 1. The compressor uses electricity to transfer heat from the building's water to the atmosphere. It's important to remember, a chiller doesn't create cooling energy, it just moves it. This is a key concept for new engineers to grasp. We know that keeping a chiller running efficiently means regular monitoring and proper maintenance. When we do this, the system uses less electricity and stays reliable for years. For HVAC engineers, understanding chiller efficiency is crucial. It helps reduce costs, optimize operations, and catch problems early. Modern variable speed chillers adjust compressor speed to match demand, improving part load efficiency. Many factors influence efficiency, from load conditions to maintenance. A higher coefficient of performance means better efficiency, lower costs, and smoother operation. This is the heart of managing energy in HVAC systems. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth.